Hello everyone. So today we are going to discuss the continuation of module 3, that is the time response of second order system and the RH criteria. So let us continue with the time response of second order system. So these are the highlighting points, that is agenda, introduction, test, input signals, response of first order, second order system response, higher order system. So then steady state error of feedback control system, stability analysis using RH criteria, then introduction to PID. So that's not required. So this will becomes under module 5. So let us discuss one by one. So how to identify the order of the system? So by using the characteristic equations, we have to identify the order of the system. So this is given by the standard equation Bm m minus 1 s to the power of m, b naught s to the power of m minus 1 and so on, divided by denominator polynomial equation. This is the general representation of second order system. So here some of the examples we are considering based on the order. So the first transfer functions, which is given by c of s by r of s, that equal to 5 divided by 4s plus 1. This denotes, if you are observing the denominator polynomial equations, the order of s is 1. So hence it is first order. For second order system, look at the denominator coefficients. The order of s is 2 to the power 2. Hence it is second order. Fourth order means the power of s will be 4. So like that, depending upon power of s, we have to consider the order of the system. So next, the type of system. So both type and order depending on the value of s coefficient. So there are the two types of system, the 0 type, type 0, type 1 and type 2. So we can call it as, here we are to consider only type 0 and type 2. So type 1 is not included in your syllabus. Hence we have to discuss the general equation for the type of the system. It is defined as number of poles at the origin of open loop transfer function, that is G of s into H of s. So number of poles. Here the in general equation, from the general equation, you have to observe that s to the power c. C is nothing but order of equation. This C denotes the type of the system. If it is 0, this is type 0. If it is 1 or if it is 2, then it is type 2. So for that observing of the type of the system, let us consider an example. So G of s into H of s equal to 50 divided by s plus 1 into s plus 4. But here the order of s is 0, s to the power 0. 0 means the value should be equal to 1. Hence we can call it as type 0. For type 1, so just let us consider the order of s to the power 1 into or s into s plus 1 into s plus 4. Then we can call it as type 2, type 1 system. Then for type 2 system, which is given by the standard equation, g of s into h of s equal to 10s square plus 3 divided by s square. S square indicate the order of s, which denotes the type of system. So hence it is type 2 system. So let us consider the main test of signals or main standard test signals, which are comes under second order system. So here the standard test signal, there are the three kind of signals which are discussed in the transient response. One is impulse function, step and ramp. So impulse function means the magnitude should be equal to 1 and it is a constant. So let us consider the impulse function, which is represented by delta of t. So this delta of t indicate an impulse signals. So this a indicate magnitude with respect to time. So in general, the impulse functions for can be represented by u of t or delta of t, that is equal to magnitude a, t not equal to 0. So for t equal to 0, its magnitude is a. If t is not equal to 0, magnitude is 0. That is nothing but somewhere here, if t is not equal to 0, let us consider t equal to 1. That is a equal to 1. Then t equal to 2. Here we get the signals. So that is the impulse function will be represented by magnitude a. Then the second step of kind of signal is step signal. We know that all the step signal will be represented like this with respect to time t. So u of t is the unit step signal. Okay. So that a step signal is a sudden change in characteristics of actual input signal. So if you are changing the limits from 0 to 1, then signal will be shifted here. So like that, the signal will be shifted from 0 to infinity. So for step signal, the value of A, magnitude is A. If t is greater than or equal to 0, its magnitude is A. Then 0 is less than 0. So if you are applying the Laplace for unit step signal, the Laplace transfer function U of s is nothing but Laplace. So for the Laplace of step signal is A by S. Laplace of 1 is nothing but with respect to 2, it is t. With respect to constant term we can retain as it is. The next kind of signal is parabolic. So this ramp signal. So ramp signal, which is a constant velocity characteristic of actual input signal. So this is the signal indicates ramp signal. R of t is the representation of ramp signal with respect to t. So ramp signal is A into t. A is the constant, t is the time varying period. So it is varies with respect to time. T greater than 0, its magnitude is kt. If t less than 0, its magnitude is 0. If you apply the Laplace for t for unit step function, it become A is the constant, we can retain as it is. T become 1 by s square. That is, after applying the Laplace, we will get the transfer function. For parabolic, this is the representation of parabolic signal. P of t is represent parabolic. For parabolic signal, it is a constant acceleration characteristics of actual input signal. This is the representation of graph. For parabolic signal, the magnitude will be represented by A into t square by 2. So for condition t greater than 0, if t less than 0, its magnitude is 0. That is nothing but the point will be here. So A t square by 2 means you can write like this. Suppose this is the point A, magnitude, it is t square by 2, that is exponential in nature. Clear? So if you apply the Laplace, A is the constant. If you apply the Laplace for t square by 2, that is you will get 1 by s cube. Okay. T square is nothing but t cube by 3. So or 1 by 2 you can keep constant. If you apply the Laplace for t square, this can be represented as 2 factorial divided by 3. That is s cube, s to the power of t minus 1. So then sum of the signal, its corresponding functions which is represented like this. So then time response of second order system. So time response of control system. So here we have to apply the input is step signal, output is exponential. So that is in the time response there are the two response curve. One is the transient response, one more is steady state response. The total response which is represented as C of t equal to CTR of t plus CSS of t. CTR of t is nothing but we know that CTR of transient response of system plus steady state response which is represented by C suffix SS of t. So this is the response curve, step response, which meets the maximum time period. So with respect to time, when the response of the system is changed from rest or equilibrium, it takes some time to settle. That is nothing but if it is in equilibrium states, equilibrium means it is steady state. This is the state is called equilibrium. Under steady state condition, the response will be constant. Rest equilibrium under steady state is the response of the system after transient response is called steady state response. So transient response, that is nothing but this is the transient response. After reaching the transient response, it reaches the steady state. This is area is called transient response of curve. You can call it as transient response, and this is TS, steady state response. Okay. So then the time response of control system, which depending upon system poles only. That is number of poles which lies in either left half of S plane or right half of S plane. Then steady state response depending on system dynamics, system type and quality of input. So which type of input we are going to apply, depending on that the steady state response will be different. So then the response of first order system which is represented by k divided by g of s is equal to k divided by ts plus 1 by t. So take the constant term t is the outside, then that t is called as order of the system. Now the unit impulse response for the first order system. So that is represented by the graphical. So then unit step response of first order system. So this is the input. So unit impulse for first order system. This is the impulse response. So k divided by ts plus 1. So r of s is equal to 1. Then to find the c of s, you can write the equation as g of s into r of s. So we know that transfer function that is equal to c of s output by input r of s. Okay. Then you have to substitute the values. You will get this equations. That is e raised to minus t by t. If you are varying the value of t, then you will get the response. Okay. Then for unit step response, the first order equation, that is c of t become like this. Unit step. So it become 1 by s. Substitute the values. Then you have to take the inverse Laplace here. So we will get c of t. So time domain, s domain become time domain. If you apply the inverse Laplace, then you have to k is the constant, 1 by s is the constant. If you apply the Laplace of 1 by s, it is equal to 1. Then t by ts plus 1 means e to the power minus t by t. So t is the constant. So similarly, response curve for the different response curve for the final values. So these are all the different response. That is t, 2t, different time period. So if you are varying the time period from 0 to capital T, so the total response, percentage of response will be increases. Once it reaches the 99% maximum value, then it is constant. That is called as steady state response. So unit ramp response. So how the graphical representation or how the graph will appear for unit ramp function. This is the transfer function of a system. If you are multiplied, the input is unit ramp. What is the overall response? If you are multiplied the unit ramp function, the response become c of t equal to k into t minus t plus t e raised to minus t by t. It's the unit ramp and ramp response. So put the value of k equal to 1 and t equal to 1 second. So we will get the nature of. So this is summarized of different inputs and corresponding different output response for the given signal. So now we shall move on to the steady state error. So the steady state error, which is given by the system is stable if one of the impulse response g of t, which is approaches to infinity, or else s tends to infinity, that is nothing but g of t, that is time domain function, that g of t is input signal which tends to 0 as t tends to infinity. That is the stable system. For steady state error, there is a difference between input reference and output. That gives a steady state error. Difference in the input with respect to reference input. You can call it as steady state error as t tends to infinity. If error is, there is a difference of errors, then the t will be tends to infinity. So let us write the block diagram. That is general block diagram for control system. So from this we know that this general transfer function. Then you can rearrange these equations. Then you will get the steady state error. ESS is nothing but final value. From the final value theorem, you have to apply the limits t tends to infinity. So limits s tends to 0. That is, as for the final value theorem, the t tends to infinity become s tends to 0. S into E of s. E of t is the error signal. If you apply the Laplace, it becomes s into E of s. So we know that E of s from the transfer function s into r of s divided by 1 plus g of s into h of s. So for the different inputs, what is the steady state error equations? So for positional error constant, then velocity error constant and acceleration error constant. These three are the different kind of inputs for corresponding time response of second order. You can step error, ramp and parabolic. For positional error constant, you have to consider the type of input is step input. For velocity error constant,